In this lecture, we're going to discuss an important concept that forms the foundation of semiconductor physics and electronic devices, that is thermal equilibrium. So, before we talk about transistors, diodes, or current flow, we need to understand what happens when nothing is happening. That may sound weird at first, but we'll see why this idea is so important. So, our learning objectives for this lecture is that by the end of this lecture, we should be able to define thermal equilibrium, identify the required conditions, explain why equilibrium is idealized, understand equilibrium as a model, and relate equilibrium to semiconductors. So, what is thermal equilibrium? So, let us begin with this simple question. What do we mean when we say that an object is in thermal equilibrium? So, at first glance, many people will think that the answer is that an object has the same temperature as its surroundings, right? That's what we concur from the name. But while that is true, it is not the complete definition. An object is in thermal equilibrium when it has the same temperature as its surroundings, and the surroundings themselves are at one uniform temperature, and most importantly, the object is free from external stimulation, right? So, in other words, nothing from the outside is disturbing the object. The object is not being heated, it is not being cooled, no light is shining on it, no electric field is acting on it, no magnetic field is present, no mechanical force such as a wind is pushing on it. So, when these conditions are satisfied, the object exchanges energy with its surroundings, but the amount of energy it receives is exactly equal to the amount of energy it gives away. As a result, there is no net change in the object's condition over time. This is called thermal equilibrium. So, let us understand this through an example. So, let us imagine a bucket of water is placed on the floor of a closed room. So the room temperature is 291 Kelvin, which is 18 degrees Celsius, or about 65 freedom degrees. So the bucket and the water are also 291 Kelvin. So let me ask you a question. Is the water in thermal equilibrium? At first, we may immediately answer that yes, because everything is the same temperature, right? But the answer might be more nuanced than that. So let us look at that. So let us consider a situation where, let's say, there's a light bulb in the room, or say there's a window and sunlight entering through the window. Although the room temperature remains 18 degrees Celsius, the light source itself uh, is considered to be much hotter. And in this case, let us just assume that it's emitting out a substantial amount of heat, right? And so the light transfers the energy to the bucket, and the bucket absorbs this energy. At the same time, it may also lose heat to its surroundings, right? So these two processes may balance each other, and the temperature of the water may or may not change. But from our definition, we remember that the object must be free from external stimulation. So, since the light is continuously supplying energy, the water is not in thermal equilibrium. So, let us consider a second situation. So, let's say there's no light bulb and we close the curtains, or there's no window. So, we switch off all the lights. Does this solve the problem? Right? But no, we are still sitting in the room. Our body temperature is around 37 degrees Celsius, much higher than the 18 degrees Celsius that we assume the room to be at or the water to be at. So, I mean, it is far fetched to say that we alone would heat up the room or heat up the water. But in this thought experiment, let's just say that it is a substantial source of heat, right? So your body continuously emits thermal radiation, and the radiation, let's just say, reaches the bucket and transfers energy to it. Therefore, the bucket is still receiving external stimulation, and it is still receiving external heat energy. So again, it is not in thermal equilibrium. So in our third case of our thought experiment, let's just say we have left the room. The room is just empty, there's just a bucket of water, nothing disturbing it, right? So lights are switched off, there's no window, nothing obvious is disturbing the bucket. Can we say that the bucket is in thermal equilibrium? So for most practical purposes, the answer is definitely yes. But here's something interesting. Even though the bucket appears perfectly still, an enormous amount of microscopic activity is still taking place. The water molecules are constantly moving, the atoms are vibrating, the electrons are moving randomly. So everything inside the bucket is still having like a crazy amount of activity. Thermal equilibrium does not mean that the atoms stop moving, right? So the water molecules are constantly moving, atoms are vibrating, electrons are moving randomly. Everything inside the bucket is in continuous motion. But does this mean the bucket is not in thermal equilibrium? The answer is no. The thermal equilibrium does not mean that the atoms stop moving. If atoms stop moving completely, the temperature would have to be 0 Kelvin, which is not possible in the ordinary situations, right? So instead, thermal equilibrium for most practical cases means that the microscopic motions are completely random. There is no preferred direction and that there is no net movement. So on average, nothing changes with time, right? So we just see the water is in the bucket and nothing crazy is happening. The distinction between microscopic motion and macroscopic stability is extremely important. So let's just say we look after a month, right? Now let's perform another thought experiment. Say we leave the bucket in the room for an entire month. When we return, we notice the water of the bucket has evaporated, like per usual. So some water vapor is now present in the air. Some would have maybe condensed on the nearby surfaces. Some has been absorbed into the surrounding materials. Clearly, the system has changed. But does this mean the bucket was never in thermal equilibrium? I mean, strictly speaking, yes. But if we use an absolute definition, right, no real object remains in perfect thermal equilibrium forever. Slow processes like evaporation continue to occur. So, does thermal equilibrium actually ever exist? In the perfect sense, no. In practical engineering, however, the answer is close enough. So, this brings us to one of the most valuable lessons in engineering, that every model has its own limitations. No engineering model is perfect. Our goal is not to create the perfect model. Our goal is to create a model that is accurate enough for the problem that we are trying to solve. So instead of asking, is the bucket truly in equilibrium? A more useful question that we should be asking is, can I model this bucket as being in thermal equilibrium for my application, right? So for example, if our experiment lasts only a few minutes, we can safely ignore the evaporation, right? It's not a substantial amount. So, but if our experiment lasts 2 years long, evaporation becomes significant and the assumption of thermal equilibrium may no longer be valid. So the suitability of our model depends entirely on the application. So why are we learning thermal equilibrium, right? At this point, we might be wondering why spend so much time studying a condition where nothing seems to happen. The reason is simple. Thermal equilibrium serves as our reference point. Think of it as a starting line before the race begins. Before we can understand what happens when we apply voltage to a semiconductor, before current starts flowing, before light generates electron hole pairs, before heat affects device performance, we must first understand the semiconductor in its undisturbed state, right? So, only after understanding equilibrium can we accurately explain what changes occur when external stimuli are introduced. So, just to summarize this lecture, thermal equilibrium means that an object has the same temperature as its surroundings, experiences no external stimuli, exchanges equal amounts of energy with its surroundings, and therefore shows no net change over time. Although atoms and molecules continue moving randomly, there is no overall change in the system. In reality, perfect thermal equilibrium does not exist forever, right? However, for many of our applications, assuming thermal equilibrium provides an excellent approximation. Finally, thermal equilibrium is not our final goal of semiconductor physics. It is simply the baseline from which we begin analyzing real semiconductor devices under applied voltages, currents, light, and heat. And over the course, we would build upon the foundation and examine what happens when a semiconductor is driven out of equilibrium. And this is where useful electronic devices begin to operate.